All right, today we're going to continue our adventures in carbonyl chemistry. This time we're going to, we're not going to be concerning ourselves with the carbonyl carbon as we did in the last video. What we're going to be doing is we're going to be moving to either carbon or each of the carbons on either side, these so-called alpha carbons. And we're going to take a look at how we can get more chemistry out of a carbonyl compound using these. All right, now one of the things, one of the first things, and this is something that you should be familiar with from issues that we talked about in the past, is this whole enol, keto-enol equilibrium. All right, as we said before a number of times, there's a kind of a natural equilibrium that exists between a ketone or an aldehyde and the so-called enol form. With the enol form, what you've got is you've got a double bond between one of the alpha carbons and the carbonyl carbon, but it turns out that the oxygen has been protonated and now you just have a single bond. All right, so this is an enol. It turns out that these enols are not very stable, so at any given time you don't really have an awful lot of this enol in the bulk of these carbonyl compounds. It's primarily in either the ketone or the aldehyde form. The thing is, what we can do is we can sort of push this process by either acid or basic catalysis. All right, let's take a look at the mechanism for each. All right, so if we take a ketone and put it into an acidic medium, the first thing that's going to happen is that we're going to protonate this carbonyl oxygen. As you would expect, we've seen that a number of times before. All right, now what happens is that as a result of protonating this, it turns out that these protons on the alpha carbons become somewhat more acidic. All right, acidic enough so that even a weak base like water can successfully come in and pull this off. Okay, so it pulls this proton off, this hydrogen off as a proton, leaving behind a pair of electrons. That pair of electrons migrates up into this bond here, chases this pair of electrons up to the oxygen, and now we have the enol. Okay, and you'll notice that the proton or the acid is catalytic because it's regenerated in the last step. All right. So if we, for some reason, and we'll see a good reason in a minute, if we want to convert a ketone into the enol form, we can push the process by acid catalysis. We can also do it by base, all right? But it's, as you would expect, it's going to be a somewhat different mechanism. Now, when we talk about base, we're talking primarily about hydroxide. And as you know, hydroxide is a fairly strong base. It's certainly strong enough to pull off some of these alpha protons. Okay, if you recall, we said that the pKa's of these alpha protons and aldehydes and ketones are somewhere between 16 and 20. Generally, the aldehydes are more acidic, so it's a little bit easier to pull off a proton off an alpha carbon for an aldehyde than it is for a ketone. But nevertheless, you can still do it with a ketone. So what happens here is that this hydroxide comes in, pulls off this proton off the alpha carbon, and now what happens, oops, what happened? Oh, are we okay?
Yeah,
all right, okay, all right. Let's see, let me reconstruct my train of thought here. Base, right, yeah, okay. So the hydroxide comes in, pulls off this proton, all right. Now we have this pair of electrons migrating here, all right. That pushes this pair of electrons back up to the oxygen so that now we have a double bond, but we've also got a negative charge on this oxygen. Now, one of the things that we've said a number of times is that when you have a negative charge on an oxygen, it becomes quite basic. All right, so it's certainly basic enough to pull a proton off a passing water molecule. All right, and thus we have our enol. All right, and once again, you'll notice that we've reconstructed or regenerated the catalyst, which in this case is hydroxide. Okay, so these are two ways in which we can sort of enhance the concentration of enols in a naturally occurring either ketone or aldehyde. All right, we can do it either by acid catalysis or by basic catalysis. All right, so that's one reactive entity that we're going to be talking about. The other one is an enolate. All right, now one of the things that you'll notice is that there's no overall charge in an enol. All right, even though we generate charges along the way here, all right, as we said before, Nevertheless, when you convert this into the enol, it's electrically neutral. All right. That's not the case with the enolate. There's one other thing that I wanted to point out with these enols. I just thought of it. These are not resonance hybrids. All right. A lot of people get the impression that this is a resonance hybrid of this. They are not. They violate the rules of resonance because you remember with resonance, you can't move atoms. The only thing that you can move around are electrons and bonds. That's not the case here, okay? Because if you compare this to this, you'll see that we've restructured the molecule. We have the hydrogen down here. In this case, over here, we've moved the hydrogen up to the oxygen. All right? Okay, anyway, getting back to the enolate. Now, the enolate, what we've done here is we've removed one of these alpha protons by a base, all right? And we've sort of installed a permanent negative charge. So the difference between an enol and an enolate is that with the enol, all we've done is we've moved around the proton and we've generated a double bond here and an OH group here. With the enolate, what we do is we actually permanently, or more or less permanently, remove this proton and we generate a negative charge on this alpha carbon. Now, the thing is, this enolate is a very, very good nucleophile. It's a soft nucleophile, and we're going to see in a little while that it's very useful synthetically. But the other thing about it is that it's very long-lived compared to other intermediates like this because this can be stabilized through resonance. All right, so this pair of electrons can move up here. You can form this double bond, chase a pair of electrons up to the oxygen, and by doing so, what we've effectively done is we've delocalized this negative charge between the alpha carbon here and the carbonyl oxygen. So this makes it a really good nucleophile. Okay. Okay, now let's take a look at one of the first applications of the chemistry involved in in generating those two intermediates, the enol and the enolate. All right. First of all, we'll take a look at acid-catalyzed halogenation of alpha carbons. All right. It turns out that if you have an aldehyde or a ketone, it's pretty easy to stick a halogen, either a bromine or a chlorine, onto one of these alpha carbons. All right. And the way it works is through the enol intermediate. So the first thing that we do under acid catalysis, we protonate this, and we actually generate the enol. Same mechanism as we saw in the previous slide. All right, now, once we've got the enol, you've got a double bond here, and this thing behaves kind of like a double bond. All right, when this gets close enough to the bromine molecule, it's going to polarize it. All right, in other words, the pi bond here is going to successfully push the electron density away from this bromine, making it electronegative, so that the pi electrons can reach out, grab this bond breaks, and now we have the bromine hooked onto this alpha carbon, and we've got a bromide ion released into the reaction mix. Okay? Now, the next step in the reaction, what will happen is that you notice that what's going to happen as a result of this new bond being formed is that this carbon is going to be left without electrons. It's going to take on a positive charge. All right, well, this positive charge on this what was the carbonyl carbon exerts a very strong attraction for lone pairs on the oxygen. So it pulls a pair of lone pairs, or a lone pair, I'm sorry, not a pair of lone pairs, a pair of electrons down into this bond here. We get a double bond, all right? That stabilizes this positively charged carbon, all right? Makes it neutral. And then in the last step, what will happen is that this OH group will deprotonate so that now we have the carbonyl restored, all right? Plus a bromine attached to one of the alpha carbons. All right, so that's the way the reaction works under acidic conditions. We can also get it to take place under base catalyzed conditions. All right, now in that case, what happens is that the hydroxide, which as we said is a fairly strong base, it's basic enough to pull off one of these protons, pulls the proton off, a pair of electrons moves up here, and we get this enolate. All right. We've got a double bond here, we've got a negative charge on the oxygen, so this thing has a true negative charge, all right? And this negative charge is going to oscillate back and forth between the negatively charged oxygen that we show here and this carbon over here, this alpha carbon, all right? Now, just to sort of keep it similar to this mechanism. What happened? We okay?
It's okay.
All right, okay, all right. All right, a glitch in the system. All right, yeah. So as we were saying, so we've generated this enolate, and just to kind of keep it symmetrical with this mechanism here, we're showing the enolate in this resonance form, right? The double bond reaches out the same way as it did over here, grabs this nearer of the bromines. We get this being formed, okay? The bromine hooks onto the alpha carbon. We've still got a negative charge on the oxygen. Pair of electrons moves down into this double bond to form a double bond here, and now we have our brominated ketone. Now, the problem with doing this reaction under base condition, or the advantage of doing it, depending on your point of view or your needs, is that this will probably keep going. You see, because what happens here is that this OH group, since it's regenerated, all right, what can happen is that it can actually come in and pull off the other alpha proton, or an alpha proton here, in which case it goes through another cycle. So I mean, in principle, what you could do is you could end up with all the alpha carbons totally brominated if you had enough bromine in the system. Okay, so this can be a blessing, or it can be a curse, as I said, depending upon what you need out of the reaction. Okay. All right. Now, probably one of the more important reactions of these carbonyl compounds using this chemistry, this enolate chemistry, involves alkylating these. All right. Now, you remember that we've said this a number of times in the course, that one of the real quests of organic chemists is to be able to make carbon-carbon bonds. And this provides us with an opportunity to make them. All right, so if we have a ketone or an aldehyde, what we can do is we can treat it with a strong base so that we fully deprotonate this. Now, as we said, when you fully deprotonate this, what you've done is you've generated an enolate. All right, and these enolates are very good nucleophiles. All right, so what can happen is that if we take this enolate that we've just generated in this step, and we expose it to an alkyl halide, preferably a primary, what will happen is that this will act like a very well-behaved nucleophile. It will come in, hit this carbon, and we will have an SN2 type reaction. And what we succeed in doing is sticking this alkyl fragment from the alkyl halide onto the alpha carbon of the carbonyl. And this is a really powerful way of making carbon-carbon bonds. The problem is that it's hard to control, all right? It's hard to control because what can happen is that if you have a strong base, what can happen is that you can actually go through several cycles of this. So instead of just getting one alkyl group attached, what could happen is that you could end up with several, right? In fact, you could end up with 2 here, you could end up with another one over here, or you could end up with 4 altogether being added on if you're not really careful with the concentrations. And even if you are careful with the concentrations, it's difficult to control it, all right? So there's actually a better method, and what it involves is that kind of weird little intermediate that we talked about a while ago when we were talking about aldehydes and ketones, namely the enamine. All right. So if we take this ketone or any aldehyde and react it with this is a secondary amine. It's called pyrrolidine. All right, and it's used a lot for this purpose, for these synthetic reactions. So if we take this along with the aldehyde of the ketone in an aqueous acid solution, what we'll get is the enamine. I'm not going to bother going through the mechanism for this because this is something that we've talked about in other places. The thing is, when you've got the enamine, it behaves just like this guy up here. All right, what happens is that this alpha carbon, or what was the alpha carbon here, is now still quite nucleophilic. All right? And what it does is it reaches out and it behaves just like the nucleophile up here. All right? It reaches out, hits this carbon, kicks out the chlorine in this case, and this alkyl group is going to hook on to this alpha carbon here, as we see over here. All right? The last step is just sort of regenerating or converting this iminium salt here that we get as a result of this reaction back to the carbonyl. And we do that with aqueous acid. All right? We get this kind of like little structure here. Okay? But this is a much better way of alkylating these carbonyls. It's much more controllable. You're only going to get one alkyl group added on, because once you form this, it turns out that this really retards any further alkylation. That's not the case up here. Okay? This is a very, very important reaction. Right? You're going to be seeing a lot of this. Okay, now another very important reaction that's related to this this type of chemistry is the aldol reaction. The aldol works best with aldehydes. And essentially what we're doing with this aldol reaction is we're capitalizing on the two reactive centers in a carbonyl compound, in an aldehyde. So in the first step, what we're going to do is we're going to convert one of these aldehydes into an enolate by ripping off this proton, right? And the standard base that we use is hydroxide. The reason why we use hydroxide is because the hydroxide will only partially deprotonate these. If you've got a whole swarm of these aldehydes, not all of them will be deprotonated by the hydroxide, because the hydroxide, relatively speaking, is not a very strong base here. As we said, this has a pKa anywhere between 16 and 20, somewhere around there. Hydroxide, if you recall, the pKa of its conjugate acid is about 15. So this isn't really a tremendously strong base relative to the acidity of this proton. So the point is that when we put this in with the aldehyde, not all the aldehyde molecules are going to be deprotonated. Not all of them will be converted into enolates. So the result is that we're still going to have some which are intact. So anyway, getting back to the sequence here. So this aldehyde here gets turned into an enolate. Now what will happen is that this enolate will seek out an aldehyde molecule which has not been deprotonated, and it acts as a nucleophile. All right? It acts as a nucleophile, and it hits the electrophilic site on the carbonyl, which we saw in the last video as the actual carbonyl carbon itself. So it comes in, hits here, and we get a permanent hookup. All right? Now, the reaction is actually quite simple. The problem is in constructing the product, because you can see that what we're generating here is a fairly complicated molecule, and you've got to get it hooked up correctly. And if you have substituents coming off these alkyl chains, you have to make sure that they're placed in the right location. The best way to do this is to number the carbons that form the main chain. So what I'm doing here is I'm numbering from one end to the point of attachment. So what we're going to get is we're going to get this hooked up over here. So I'm going to count 1, 2, and then I pick up the count at the other point of attachment, 3, 4, 5. Right? So this does two things for us. First of all, it tells us that we've got a 5-carbon chain. Right? That's the basic skeleton of this new molecule. It's got 5 carbons. And the first thing we do is we draw a 5-carbon chain, 1, 2, 3, 4, 5. And then we just transcribe these numbers over onto that alkyl chain. Then you go back to the 2 components and you see what's hooked up to each one. Now in carbon 2, you see we have this aldehyde group, right? So we stick the aldehyde group onto carbon 2. Okay? On carbon 3 over here, when this reaction takes place, this oxygen is going to become negatively charged. It's going to chase a pair of electrons up here, all right? And ultimately, this will get protonated. It will turn into an OH group. So we stick this on carbon 3. We don't have any other substituents, any methyl groups or halogens coming off 4 and 5. So that's basically it. This is still a relatively simple molecule, all right? But anyway, that's the way this reaction takes place. First, we form an enolate of one of these aldehyde molecules. That, in turn, attacks nucleophilically an aldehyde which has not been converted into an enolate. All right, so you have this hooking up, or rather this hooking up with this, and you end up with this larger molecule here. All right? And once again, this is a very, very useful way of making carbon-carbon bonds. Now the thing is, we could take this one step further. If we take this aldol product, all right, we take this aldol product, well, this aldol product here, which consists of an aldehyde group and an OH group. What we can do is we can eliminate this OH group. Right? We can eliminate the OH group by an elimination reaction, either under basic conditions or acid conditions, if we add a little bit of heat. Now, one of the problems that you remember from our discussion of alcohols earlier in the course was that when you have eliminations resulting from dehydration, in other words, an OH group along with a proton, in a case like this, it's hard to tell which side. In fact, in a lot of cases, it's impossible to tell whether the double bond is going to form here or on this side over here. With these, it's a no-brainer, right? Because what has to happen is that the double bond has got to form in such a way that it's conjugated with the carbonyl, because you're going to get a lot more stability out of that. So to answer our question, the elimination is going to take place across here. This is going to be our final product, right? And you can see that this double bond is going to be conjugated with the carbonyl, and it will be a lot more stable as a result than if we had the double bond forming over here. So this is the aldol addition reaction and the aldol condensation. All right, and once again, this is a very, very useful reaction. Okay, now one of the problems with the aldol is that you have to use one, in most cases, you have to use one aldehyde. For example, if we used this mix here, where we have propanal and butanal, we'd end up with 4 different products. All right, we'd have this combining with itself, we'd have this combining with itself, that would be 2 products. We would have this enolate combining with this enolate, that would be a 3rd product, and then we would have this enolate combining with this carbonyl here. That would be the 4th product. So this would be a mess, all right? This would not be practical, because if you get 4 different products, it's going to be really, really difficult to separate out the one that you really need. Now, some that will work, all right? There are some that will work. Like, for example, this guy here. You can easily get one product out of this, because you notice that you can't form an enolate here. Remember, the absolute requirement for enolate formation is that you have to have a proton coming off one of these alpha carbons. So in an aldehyde, you've only got one alpha carbon. This is a T-butyl group, so we don't have any hydrogens here. So you can't form an enolate here. This, on the other hand, can. So this is going to be the only enolate that we get. This comes over, hits this carbonyl, and this is going to be the product that we get. And I left out the OH group here. Stupid, okay? You should have an OH group here. Write that in right now. Okay, now, finally, the last variation on these aldols. Now, as we said, you can't, generally we don't use ketones, but in this particular case we can, all right? This is an intramolecular aldol. And you notice that we've got 2 carbonyls at either end of the molecule, right? They're both ketones. And in this case, the reaction will work, all right? Now, the other thing about this is that if you do one of these intramolecular aldols, you have to make sure that the compound is symmetrical, all right? If the compound is lopsided in any way, all right, what's going to happen is that you're going to get 2 products, all right? That's not the case here. If you notice that these substituents are both symmetrically placed from both of the carbonyls, all right? Now, what's going to happen is we're going to take base, just as we did with the, with all the other aldols. It's going to deprotonate one or the other. In this case, because of the symmetry of the molecule, it doesn't make any difference which one. All right, so let's just pick this one. Pulls the proton off this. We get this enolate. All right. Now this enolate is going to come over and it's going to hit this carbonyl on the other end. All right. And once again, using our trick of numbering, it takes a lot of the guesswork out of figuring out what the final structure of the product is. So we've got, we count from one point of attachment to the other point of attachment. So it's 1, 2, 3, 4, 5, 6. All right. That means that we're going to have a 6-member ring. All right. So we draw a 6-member ring, put the numbers in, and then we just go back and we just add on the substituents that come off each of the carbons. So off carbon 1, we've got this ketone group, right? So we stick that on. Carbon 2, you see that we've got a methyl group, we put that on. Carbon 4, we've got another methyl, put that on. And then at carbon 6, we've got this oxygen, which is going to turn into an OH group, and we have another methyl group. Okay, so we've got that. All right, that's the product. You see, and that's the benefit of numbering these things, because number one, you know how big the ring is going to be, and number two, you know where everything goes, all the substituents go. Now, just to round this out, if we take this now in either an acid or a basic medium and heat it a little bit, what will happen is it will get the condensation. In other words, we'll get the dehydration reaction, and obviously the dehydration has got to take place across bonds 1 and 2, because that will give us a double bond which is going to be conjugated with the carbonyl double bond. Okay? So this is sort of like a quick introduction to this enolate chemistry. We're going to see more of this, all right? We're going to see later on in the course that with compounds like esters, we can get a similar type of reaction. Well, not somewhat similar, all right? Because esters can also form enolates. The reaction is going to have some significant differences, though. All right, thanks for your attention. I'll see you in class.